go grab something to eat and then come back. We'll see you at 12 o'clock for a presentation from Professor Lisa Kewley. So welcome back everyone to our depth study. I hope you had a nice little lunch break there. In a moment, I will introduce our next speaker. We have Professor Lisa Kewley, which we're very honored to have. Lisa recently received a pretty big international award, which was the James Craig Watson Award. So this award is pretty up there with regards to awards that are given out in the field of astrophysics. So congratulations on that award, Lisa. Lisa received that award earlier this year, and that was a pretty big deal for Lisa and the work that she does and her team and ANU and other universities that she collaborates with. So thank you very much, Lisa, for joining us, and I'll hand the screen over to you.
Thanks, Matt. Thanks everyone for joining me. Today I'm going to be talking about the history of oxygen and some of the work that we've been doing in that field. So I'm just going to share my screen so you can see my slides. Matt, if you can let me know when my screen is now visible to everybody.
Yes, that's perfect, Lisa.
Excellent, thanks very much. Okay, so today we're going to go on a bit of a romp through the universe, and we're going to follow oxygen atoms from when they were born in the universe to the oxygen that you're actually breathing right now. So first we're going to start with oxygen. Why do we care about oxygen? Of course we breathe it, and we actually breathe a lot more oxygen than you'd think. So an adult inhales about 0.05 to 0.1 ounces of oxygen a minute. And it doesn't sound like very much, but in a year, an adult actually inhales a ton of oxygen. And kids, depending on their size, will inhale, maybe half of that or 2/3 of that or a quarter of that. And so if you can imagine how much a ton weighs, well, sometimes it's hard to think of how much a ton weighs. So I like to put it into physical terms. So it's about the weight of a rhinoceros. And so we are actually breathing an enormous amount of oxygen. Why do we need so much oxygen? Well, the chemical reaction that's happening in our bodies is that we are combining glucose, which is sugar, and that comes from our food. We combine that with oxygen in our bodies, and then we turn that into carbon dioxide, which we breathe back out through our lungs, water, which our body uses for lots of things, and then energy. And it's the energy that's actually the critically important thing here, because we're basically converting oxygen into energy, and we're using energy for everything we do. Now, part of our energy is actually used, and most of it is actually used by the brain. So the brain uses more energy than any other organ. It's basically split up amongst all of our organs, and the brain uses about 20%. So if you're thinking a lot, then you're using more oxygen actually. Now, when we talk about oxygen that we're breathing on Earth and using to create energy in our bodies, we're talking about the oxygen molecules. And so the oxygen molecules are two oxygen atoms that are combined together. And those two oxygen atoms share electrons. So you have the oxygen nucleus there, you can see in pale blue, and the electrons that are surrounding those atoms are in red in one oxygen atom and blue, dark blue, in the other oxygen atom. And they're actually sharing the electrons, and that's how they join together into the molecule. When I talk about oxygen in the universe, I'm going to start with the oxygen atom, because we can't get the oxygen molecule without creating the atoms first. So here's an oxygen atom. So in the nucleus, you've got neutrons, 8 neutrons and 8 protons, and then surrounding that, you've got 8 electrons. And so we have to somehow create that oxygen in the universe. So this is a short history of time. So what we have is we've got the Big Bang, and then after the Big Bang, we went through a period called the Dark Ages, and you can see it's dark here in the left part of this cone plot. And in that time, the universe expanded in darkness, and the Big Bang created hydrogen. So all the hydrogen in the universe was created by the Big Bang. And then a little bit of helium was also created in the Big Bang. and then the rest of the elements were created after that time. And so during the Dark Ages, we just had hydrogen and a little bit of helium in the universe, and then the stars and the galaxies were formed later. So how did that actually happen? If we only started with hydrogen and helium, how did we get everything else? So the universe, the Big Bang, started 12 to 14 billion years ago when the universe was only a few millimeters in size. So the universe was actually smaller than your little fingertip. And then suddenly the universe started expanding, and we can think of the expansion of the universe as basically the distance between things. So the distance between the hydrogen atoms just suddenly got bigger and bigger and bigger. So the atoms themselves didn't get bigger, but the distance between them did. And it's still happening today, that the distance between things is getting bigger and bigger. And so we think of the Big Bang as basically the simultaneous appearance of space everywhere in the universe, and that space then began expanding. Now, in the early universe, as I said, we just had hydrogen and a little bit of helium. And what happened was, due to the gravity of those little atoms, they collided together and formed puddles of gas. And so we think of them as sort of puddles. It's basically just gas clumps forming together in the early universe. And so as the clumps got bigger and bigger, they got more gravity, and they were able to attract more hydrogen and helium together to form bigger and bigger clumps. And so this is actually a zoom into the densest clump in a simulation done on a supercomputer. So we're zooming into gas here. So this is, let's do that. We'll do that movie again if we can. Yeah, we're going to zoom in right to the center. And this is the really dense clump in the universe. Now, it's in these dense clumps that the first stars were forming. And I'm going to show you a simulation of what we think the early universe looked like based on big supercomputer simulations that are done here in Australia. And the universe, first it was, you couldn't see through it. Basically, the hydrogen and the helium atoms would have absorbed all the light, any light that was emitted. So first there was darkness, and then the first stars formed in the densest clumps of the universe. And so stars form when gas is really dense, and it basically just collapses, and then a star forms. When that star forms, what happens is that it lights up the universe, and it actually rips electrons off the atoms that are surrounding the star. And that means that you can actually start to see through the universe. So this is what it looked like in the early days of the universe. The red is the hydrogen atoms, all clumped together, very big clumps. And the little white things you can maybe start seeing in the holes, they're the first stars being formed, and they're ripping electrons off the atoms, so you can no longer see these clumps. And then you start seeing the stars in the universe. The hydrogen's still there, it just doesn't have those electrons around it later on. Okay, so inside those first stars, some chemical reactions happen. So this is a fusion reaction. So hydrogen fuses together to form helium, and then oxygen's created through this process where you've got two helium atoms are fused together to form beryllium, and then you add another helium atom to form carbon. You add another helium atom, and then you get oxygen. So this is one of the main ways that stars like our sun will in future be able to make oxygen. Our sun currently is only turning hydrogen into helium. So this is a sort of a process that happens in a little bit more evolved stars. Okay, so how do we get oxygen out of stars? Oxygen is actually blown out of stars in a few different ways. So one way is that you get a supernova, and when a star has a supernova, it needs to have a mass, quite a large mass, and so it basically stops being able to fuse atoms together in the nucleus. What happens is you get to iron, so that all the atoms are fused together to form new chemical elements. But it stops at iron because it actually takes more energy to fuse iron than it does to just stop. So the stars just stop at that point. Now the stars are actually being held up by the fusion reaction. The fusion reaction is creating energy which is holding the star up against its own gravity. So when those fusion reactions stop, what happens is the star then begins to collapse. the outer layers basically rebound, and so the star blows off its outer layers in a supernova, but the core keeps collapsing, and then you end up with a neutron star, or if the star's massive enough, you end up with a black hole. And so when the star blows off its outer layers in a supernova, you actually get oxygen being blown out of the star in this way. So this is a real image of a supernova. This is taken in the X-rays with the Chandra X-ray satellite. And this is, the different colors here correspond to different elements. So you've got oxygen is blue, and then the other colors correspond to neon, magnesium, silicon, and sulfur. You can see there's actually quite a lot of oxygen in this supernova, and this is one of the few known oxygen-rich supernova in our Milky Way. Another way that oxygen is blown out of stars is that massive stars blow material away just due to the fact that they're really unstable. So really massive stars that are fusing helium together to form carbon or nitrogen or oxygen, they're pretty unstable in their outer layers. They actually expand and then contract and expand and then contract because these fusion processes create lots and lots of energy. And so these stellar winds that are blowing material off these massive stars can be up to 200 kilometers per second. So this is much more than our cars can even go. And so once oxygen's in the gas, then we're able to observe it through the universe. And so there's a few different ways we can observe oxygen. And the easiest way to do it is to use an emission spectrum, which is the one in the middle here. So we get a hot gas, so the universe is full of hot gas around stars, and we put it through a spectrograph, and it's like putting light through a prism, and it splits the light into its different colors. So you can see the colors of the rainbow here. This is because the light's been split into different frequencies. And right at the left, that red line there, that is a hydrogen line, and right at the right in the blue, very blue, far blue, you can actually see two oxygen lines. And so these are the oxygen lines that we use to measure the amount of oxygen in galaxies in the universe. So we're using this type of spectrum. And so how do we measure the amount of oxygen in the universe? We need to look back in time, but in astronomy we can look back in time because the light that galaxies emitted actually takes billions of years to reach us. So these are real images of galaxies using the Hubble Space Telescope. And in the top right image there, the light from these galaxies took 7 to 10 billion years to reach us. So we're actually looking back in time 7 to 10 billion years ago. Those galaxies were very clumpy and lumpy. And then galaxies that were where the light took 3 to 7 billion years. So we're looking back 3 to 7 billion years ago, begin to look more like the Milky Way. They've got disks, they've got spiral arms, and then galaxies close by look much more like our own Milky Way. And so how do we look at the most distant galaxies? Because they're really, really, really faint. And we even with our largest telescopes that we have on Earth or with our largest space-based telescopes, they look like tiny little dots, and it's really hard to measure. So we actually need to do better than our current telescopes. And so what we use is a really nifty technique called gravitational lensing. And this is a technique that was predicted by Einstein and only proven much, much later that it actually does exist in the universe. Einstein predicted that if you have a really massive object in the universe, like a cluster of galaxies could be a really massive object, or a quasar is a really massive object, then you can actually bend the light around that massive object, and the light bends just due to the gravity. So gravity attracts everything, including light, if the object's massive enough. So it doesn't happen on Earth. Earth's not big enough, but a whole cluster of galaxies and the dark matter that's in those galaxies is enough to bend the light. And when the light's bent around like this is actually the same as what's happening in a refracting telescope or through lenses, like in a magnifying glass or in glasses. And so we can actually see the light of the distant galaxy, and it's amplified, so we can see it brighter than what it would be otherwise. And it's also, the light is stretched out on both sides, and the stretched out light means that we can actually see where the oxygen is in the galaxy. It's not just a dot anymore. Now, the problem with lensing is it actually distorts images. So if you have a glass, just a regular glass on Earth, and you're looking at the light through that glass, say you pick the glass up and you look through the bottom of the glass, everything's going to look kind of weird and distorted, and sometimes the light looks like curved. Something that's not curved looks curved. And so that's what happens to the light of the galaxies. It actually gets distorted and curved. And I'm going to show you a real lensed image here. So this one is a nearby galaxy cluster that we use to look at distant galaxies. This is a Hubble Space Telescope image. And the bright galaxies here that you can see are all the cluster galaxies. So they're nearby. They're the ones doing the bending of the light. The ones behind, which look kind of like lines, those ones, you might be able to see them, they're arcs and lines. They are the lensed galaxies, and that's how we find them, because they look like something that's been really stretched. And those galaxies, actually the light emitted by them is anywhere between 6 to 10 billion years ago. And so we're looking at those galaxies 6 to 10 billion years back in time. I'm going to show you an example of gravitational lensing, what would happen if a lens is on Earth. So this is the Smithsonian Natural History Museum. This is a museum in the US. Now I'm going to put a quasar in front of it, and we'll see what happens to the image. This is a good image to lens because there's different parts of it that you can see what happens to. So this is what would happen if we put a quasar in front of that building. You can see that the two towers of the building are stretched around. And in the middle, there's something funny. You've actually got a second image of the whole thing. It's upside down. And so you've got a second image of the sky upside down and a second image upside down of the two towers and the building. And so this is what happens to galaxies when they're lensed as well. And I'm going to show you another example. This is our Shine Dome. Those of you who've been to Canberra or are based in Canberra might recognize this building. And this is an interesting one as well. If we put a quasar in front of this, that's what it looks like. And so it gets really distorted. And the little blue circle inside there is actually another image of the sky, and it's also distorted and upside down. So these are real images of gravitationally lensed galaxies in the universe. And astronomers really like to name their gravitational lenses funny names. And so the one on the top left is called the Cheshire Cat, and we've got bullseyes, and we've got an Einstein cross, and we have a cosmic eyelash, and then we also need to have a cosmic eye. And all of these are real images of one galaxy behind, but what's happening is it's actually been distorted. It's spread into either a circle, or you see multiple images of that galaxy. These days, with supercomputers and very good observations of the galaxy cluster, we actually can estimate very accurately the effect of the gravitational lens on the image of the galaxy. We can actually correct all that out. And so what we do is we look at these gravitational lenses with the Hubble Space Telescope, and also the biggest telescopes in the world, including these Keck and Subaru telescopes. And so I used the Keck and the Subaru telescopes in Hawaii to do my studies on oxygen. And what we discovered was that the oxygen atoms, almost all the oxygen atoms in the universe, were actually created very, very, very early on. And so right after the Dark Ages, the first stars formed, and then the first galaxy formed. And that's about, 400 to 600 million years just after the Big Bang. And that's when we think most of the oxygen in the universe formed. And so when I looked at oxygen in galaxies using this gravitational lensing method, that's what we found. And we found that over the past 6 or 8 billion years, oxygen's actually only been rising very, very slowly. It hasn't been created that much. And so what does that mean? That means that most of the stars that were ever formed in the universe were formed very, very early on. And that these days, there are still stars being formed in galaxies, but it's the majority of that happened much early on in the universe. So the early universe was a very, very exciting place. Okay, now the question is, how did the oxygen get on Earth? Because we've seen that oxygen is created in stars, and then the stars blew that oxygen out using supernova and stellar winds. And how did that get into planets? So we know that stars formed in disks. Planets formed in disks around young stars. So early stars were always spinning, and they're still spinning. We can actually see young stars around us today, and they're spinning. So stars made of gas and dust, and this is actually, if a star's spinning, then it will always form a disk around itself. And so the very early stars have a disk around it. Now, because there's all this gas in the disk and dust in the disk, then because of gravity, the dust and the gas start colliding together and forming clumps. And then as it moves around, as that clump moves around, it basically carves out a path in the disk. It carves out a hole. And you can see here there's rings. And so where it's black, that's because a planet has carved out a hole in the ring. And it basically just accumulates more and more gas and dust from the very early star, we call protostars. Now, how did planets form how do we get oxygen on planets in our solar system? So about 4.5 billion years ago, the Earth began to form in a disk around the sun. And so we had dust and gas in the disk, and then the Earth was forming, and it basically carved a hole, and then the dust and gas, because of the gravity of the Earth, it attracted more dust and gas and became a bigger planet. And there's a question is, was there oxygen in the Earth's early atmosphere? I'm going to let you have a think about that. Of course, I can't hear you say your answer, but you might want to say the answer, what you think is the answer to your classmates, or if you're online, you can have a think about the answer. Was there oxygen in the Earth's early atmosphere right after it was just formed? No, there was no oxygen at all in the Earth's early atmosphere. So the Earth, it was only 2.5 to 1.6 billion years ago that oxygen started appearing in the atmosphere. So there was about 2 billion years where there was no oxygen in the history of the Earth. So the Earth, almost half of the Earth's history, there was no oxygen at all. And so how did the oxygen even first start appearing? Well, the bacteria in the oceans made the first oxygen. So the oxygen was already there in the gas and the dust and stuck inside the oceans and also in the rocks in the Earth and not in the atmosphere. But the bacteria started forming in the oceans, and this is and there was bacteria called cyanobacteria which started forming the first oxygen. They look like kind of tiny little circles. And we know that because we can look at fossil records, and there's fossil records from old ocean beds that we can look at, and we can actually see the cyanobacteria in them, and these fossil records are called stromatolites. And we can also date these stromatolites, so we know when those oxygen atoms were first starting to form. Now, the oxygen, when it first started forming, it reacted with methane, which was in the Earth's atmosphere. And the methane is made of carbon and hydrogen, and that was keeping the Earth warm. So methane is a greenhouse gas. So the early Earth was actually quite warm. And the reaction that happened is actually the same as lighting a gas stove. So oxygen reacts with methane, and it actually caused the first ice age. So because there was less methane in the Earth's atmosphere, which was keeping the Earth warm, it actually caused the temperatures to drop dramatically. So this is the first ice age was before there was life on Earth. There was just bacteria. So before life as we know it, it was there wasn't any creatures like this here in the Ice Age movie. And it almost wiped out all the cyanobacteria actually. So there was hardly any left there. So in the stromatolites, we know that there was a period where there were very, very few cyanobacteria. We're very, very lucky that a small amount of bacteria did survive, and it kept creating oxygen. And then finally, we have the amount of oxygen that we have on Earth today. And so I think that we're really lucky to be alive on Earth today. So I'm going to do a quick summary of what we talked about. So first, we started with the Big Bang. So in the Big Bang, it created all the hydrogen in the universe and a tiny little bit of helium. And then those hydrogen and helium atoms, they collided together in sort of puddles, and they became small clumps and then big clumps of gas. And the biggest clumps of gas then collapsed to form the first stars. And it was in those first stars that the first oxygen started being made in the universe. And we know now from our observations using gravitational lensing that this is really when lots and lots and lots of oxygen was being made in the universe. We don't see oxygen unless it's actually released from the stars. And so stars release oxygen in two ways. They do that through supernovas. So massive stars have supernova where they blow out oxygen from the outer layers. And also stars have massive stellar winds, and these stellar winds can be up to 200 kilometers per second. Now, so then you've got gas sitting around, which has been blown out of stars that already has been enriched with oxygen from those first stars. And then this process happens over and over and over and over again through about, 13 billion years in the universe. Over and over again, you've got star formation from dense gas clumps, oxygen being made in those stars, being blown out of those stars into the surrounding gas, and then that gas then collides together to form big clumps, and then those clumps collapse to form new stars. Those stars have supernova stellar winds. That material that's blown out is then more enriched with oxygen, then forms more stars, and it happens over and over and over again in the universe. And it's in the gas and the dust, which are leftovers from star formation, that where planets are formed. And so because the gas around our early sun had oxygen from previous generations of stars, that's how we actually managed to get the Earth forming with oxygen inside it. But oxygen wasn't in the early Earth's atmosphere. It was actually made by cyanobacteria, and we can tell that from the stromatolites, the fossil records in rocks. And then finally, the amount of oxygen that we had on the Earth, it increased, but then it reacted with the early methane in the Earth's atmosphere, which was keeping the Earth warm, and it caused the first ice age, and it almost wiped out all of the cyanobacteria. Fortunately, there was a little bit left, which was able to make enough oxygen that we can now have the amount of oxygen we have today. So we're lucky to be alive. So I get you to take a deep breath. The oxygen atoms that you're breathing are between 11 to 13 billion years old. They actually really are. They were created in stars in the very early universe, and then were thrown out of those stars in massive explosions. The oxygen catastrophe, which is where the oxygen reacted with methane and caused the first ice age, it almost wiped out all life on Earth. So I think we're actually really lucky to be alive. Now I'm going to show you a movie of the next generation Hubble Space Telescope, and this space telescope is going to be called the James Webb Space Telescope. And this telescope's due to go up next year. You'll be able to watch the launch online, and it'll probably be on TV as well. And this space telescope aims to look at the first stars and the very first galaxies in the universe. And we expect this telescope to be able to see how the oxygen was first forming in the universe, in the first stars and the very first galaxies. We've never been able to see the first stars and the first galaxies before. So as astronomers, we're really, really excited for this James Webb Space Telescope. So I'm going to show you a movie of what's going to happen after launch. So this space telescope is about the size of a bus, or a few buses actually joined together. And it needs to be very, very compact, or long and compact, because it needs to be launched inside a rocket. Once it's launched, then the rocket pieces disappear. They basically are just thrown off into space. And then the telescope itself can unfold. And it needs to unfold quite a lot because it has to be so compact to be launched. So I'm going to show you the movie of what happens now after it's launched into space. So this is solar panels, which are giving the telescope the energy. The little thing at the bottom is the radar, which sends the signals back to Earth of the space telescope data. What's opening up now are the solar shields. So these are shields which protect the telescope from the very high energy rays from the sun. The sun can really damage these sensitive telescopes, and so you need to protect them with special shields. And so these shields need to unroll. They need to be quite big because they have to protect the whole telescope. They also need to be quite light because you don't want them heating up and then heating up the space telescope. And so they're actually made of really amazing lightweight material, very shiny, to reflect the light as well. And to keep them cool, the shield's actually been split into actually lots of very, very thin shields, which are opening up a bit like an accordion here. And that's to let airflow through them so that they can cool themselves down. Now we've got the mirrors opening up. So we've got the primary mirrors, the really big one there, which has hexagons. And now we're just going to do a bit of a zoom around the James Webb Space Telescope and check out what it looks like. There's the solar panels. We're looking at the bottom of the solar shields. And you can see a tiny little mirror right at the top of the telescope there, right out the front. That's the secondary mirror. So the light bounces off the big mirror and then it's reflected off the small mirror and then back into a hole in the telescope in the center, where the light goes to the images. Now this space telescope is only an infrared telescope. So it's looking at the infrared part of the spectrum, and the reason why it's only infrared is because the light that we see from distant galaxies, the light's actually shifted towards the red. So the oxygen lines that I showed you that are blue, in the distant galaxies, they're shifted towards the red because everything that is expanding and moving away from us, its light is shifted to the red. And this is called the Doppler effect. So this even happens on Earth. If you listen to a police siren or a train horn and where something's moving away from you, then the frequency of that goes down and it starts to sound really funny. One time I was driving past a farm and there was a rooster crowing and I was driving pretty fast, and so the rooster went cock-a-doodle-doo like that, and that's the frequency of the light becoming lower and lower as it's moving away, or I'm moving away from it. This is what happens in space. So we need to have infrared instruments on a space telescope like this one, because infrared's actually created by anything that's heated up. So your bodies make infrared light, and also our atmosphere is very, very good infrared source, and also our Earth, because it's being heated up by the sun. So it's very hard to do very sensitive infrared astronomy on Earth. So we're excited, and keep an eye out for new discoveries with the Hubble Space Telescope, and we're going to be discovering a lot more about oxygen in the universe. Okay, so I think I'll finish there and go to questions. I'm sure people have a lot of questions. I'm going to stop my screen sharing. Okay, so I'm going to look at the Q&A and I can see some questions here. Okay, there's a question from Nick. Does gravity from celestial objects affect spectral lines? So the gravity does affect actually the amplitude, so the strength of the spectral lines. They might be small lines or they might be large lines. And so the gravity actually, because things get brighter, it makes them bigger. And that's very helpful to us because we're measuring a blue oxygen line. And so it actually becomes brighter. It's much easier for us to measure. Got a question here from Justine. We're a bit confused by one of your graphs that showed water was there before oxygen. Yes, so water was there before oxygen. And so the oceans were created on Earth before oxygen. And how the oceans came on Earth is actually a real mystery. Astronomers don't even really understand quite how all the water came to be on Earth. a lot of planets are icy planets because they were formed further out in the solar system where the hydrogen and the oxygen were able to collide together and form water which froze immediately to form ice. On Earth, we're closer in, but we do have ice on our poles. And so we think that in the very early days when the Earth was forming, you did have oxygen there and hydrogen there, which then collided together and you get ice. But we think that there's too much water on Earth to be formed just in that way. We think that lots of the water on Earth actually came from comets, asteroids, very icy bodies that impacted the Earth very early on. We think that the early days in the solar system, there was actually a huge amount of impacts from icy objects, and that this is how a lot of the water was brought to Earth. But it's still an open question. There's lots of astronomers in the world studying how the amount of oxygen and the amount of water came to Earth. So there was water there in the oceans already, and that means that there was the ability for life to form within the oceans. So when we look for life on other planets, we're actually looking to see whether there's liquid water, because we think that it's actually a very good environment for life to form. And bacteria is really a very simple form of life. And so that's what created the first oxygen due to photosynthesis. Okay, we've got a question from Elijah. If the universe is expanding and there's nothing outside the universe, what does the universe expand into? That's a really good question. Nobody knows. Some astronomers think there are multiple universes. I think there probably are multiple universes too, because when we look at the mathematics and we do supercomputing simulations of the mathematics of the universe, it looks like there could have been multiple Big Bangs. And so there might be other universes out there. And so we might be expanding into some space where there's other universes also expanding into that space. Now, it's interesting, while the universe is expanding, it really isn't expanding into like space that like we have in our own universe. So the way we're expanding is it's the space between things that's getting bigger. So if you imagine these are two galaxies and the universe is expanding, the galaxies themselves aren't getting bigger, the space is actually itself is expanding. So it's actually, we're just creating more space. And the universe doesn't really have an edge. So everything in the whole universe is expanding away from everything else in the universe. So if we were on another galaxy or another planet in another galaxy and we look at the universe, and on that galaxy, we also would think that everything's expanding away from us. Here on Earth, we see everything expanding away from us. Everywhere else sees everything expanding away from them as well. And so in that sense, the universe doesn't really have a center and it doesn't really have an edge, because the space is being created between things everywhere. It's really hard to wrap your head around that one. How does the Space Telescope cool down with air if space is a vacuum? So the Hubble Space Telescope, it actually uses the solar panels for moving. So it does move itself. So it slews and it has to actually rotate around. And it does this, it does it very slowly so that it doesn't, create too much heat or, cause damage to the telescope. It uses gyroscopes, so spinny things, to be able to do its pointing. And so it does move around a little bit. And so it does need to have space between those solar shields. And there is some movement, which helps it cool down. You don't want to have a really thick thing to be absorbing the light from the sun, because that will actually keep emitting heat for a long time. If it's very thin, then it can actually cool down quickly into space. Now, the Hubble Space Telescope's not in pure space. So it's in our solar system, and our solar system's sitting inside the arm of our Milky Way galaxy. And so there is atoms which are in space, which can help cool down things. So it's not like the air on our own Earth, but there's still some atoms there out there. Okay, so there's a question from Gita. you mentioned that oxygen is 13 billion years old. So will it ever run out or finish? And if so, how long? So yes, we think that it will still be there, but the stars are eventually going to stop forming. So when we measured the expansion of the universe, we noticed that instead of just expanding at a constant rate, everything's actually accelerating. So the expansion rate is accelerating, which means that instead of moving like this, everything's actually going like this, moving faster and faster and faster. And because the universe is moving faster and faster and faster, it means we get less galaxy collisions and gas collisions in future. So when we look at early galaxies in the universe, we notice that there's lots and lots of galaxy collisions. And you remember that Hubble Space Telescope image that I showed you of the galaxies that where the light was, emitted 11 to 12 billion years ago. And those galaxies were really clumpy and lumpy. Those clumps and lumps were really massive star formation happening in those galaxies. And that was happening due to all the galaxy collisions. And so if galaxies are colliding together, then the gas collides together and you get more dense clumps which are able to form into stars. And so in the early universe, there was lots of collisions, which meant that lots of gas colliding together to form larger clumps of gas, which were able to collapse to form stars. In future, because the galaxies are moving further apart from each other, we're going to have less collisions, so less ability for the gas to collide together and less stars forming. So in the very distant universe, and this is, billions of years in the future, it's something we don't need to worry about. The stars will stop forming and the atoms will still be there, but they won't be lit up by stars. Okay, I've got a question from Emmanuel. Which part of the Big Bang was it, again, where most of the oxygen in our universe were created? Okay, so the Big Bang created hydrogen and a little bit of helium, and that's it. So that was created by the Big Bang itself. And then after the Big Bang, that hydrogen and helium started colliding together to form puddles of hydrogen and helium gas. And when those puddles got big enough, or those clumps got big enough, they collapsed to form the first stars. And it's in those first stars that the first oxygen was formed in the universe. Okay, so I think that's all those questions. Feel free, I think we've got a little bit of time, so please feel free to ask more questions.
Lisa, can I just ask you, obviously you're now based in Canberra ANU, but can you tell us a bit of your path to how you got to where you are? So, sure. Sort of your high school to ASTRO 3D director sort of journey?
Yeah. So when I was in high school, I got interested in astronomy because I got a book of galaxies. And it was a book and it had some of the first images from the Hubble Space Telescope in it. And I just thought they were beautiful. Like, I really liked the look of galaxies and I wanted to understand them. And so I did physics in high school in year 11 and year 12. And I told my teacher that I was interested in astronomy. And so he told me some astronomy books to read. And I really liked reading about things like black holes and got interested in those. And my high school physics teacher took us on an astronomy camp because he liked astronomy and he loved astronomy, and he had his own telescope. So we got to look through the telescope and see the moons of Jupiter. And we actually did it for multiple days, so we could actually see the moons were moving pretty fast, and they're in different positions in different days. And we tracked how the constellations move across the sky, and made our own sundials so we could tell our own time without a watch. We had to test them and see if they really worked, and lots of other astronomy experiments. So that got me really interested in astronomy. But we didn't have any astronomy in school aside from that. And so I did physics and chemistry and maths in high school and English, and then I did French as well. And I also went to the National Science Summer School, which is now called the National Youth Science Forum. And this was a really good opportunity to meet other kids that were interested in science, because there weren't that many in my high school. I went to Banksia Park public high school in Adelaide. And that was a great opportunity, and we did an excursion up to Mount Stromlo Observatory, which is in Canberra. Anybody can come up to Mount Stromlo to visit. There's a visitor centre there, and there I was able to see that there are astronomers working, and that you can actually get a job in astronomy. So that's when I decided I'd like to be an astronomer. So then I applied for a Bachelor of Science at Adelaide Uni. And you couldn't do astronomy as an undergrad then, but you can now. So I did physics and maths and a little bit of chemistry. And then I applied in my second year of uni to go to Mount Stromlo for a summer. They've got these summer scholarships, which they pay you to come up in the summer, and you stay in the colleges on campus, and then you come and do a research project. And so my research project was it was actually the comet that hit Jupiter. There was a comet that hit Jupiter, and my supervisor had taken infrared images of this. And my job was to reduce the images, which means you got to remove all the crap that is brought into the image from things. So for example, the atmosphere makes infrared light, and the telescope itself does, and there's reflections around the telescope. The electronics actually create noise that you need to take out too. So I did that, and then so the image started off looking black. You couldn't see anything. I didn't think there was anything there. Once I'd taken out all of this extra infrared light that's being produced all around the place, you could suddenly see the Jupiter, and then the comet coming, hitting Jupiter, and then there's some dust is blown up from Jupiter, and so I was able to measure, what's coming out of that dust impact. I thought that was fantastic. So after I did my undergrad, I then applied to do PhDs in astronomy, and I came back to Mount Stromlo because I had a good time as a summer scholar. And then after I did my PhD in colliding galaxies. So I looked at luminous infrared colliding galaxies, and I wanted to understand how the amount of stars for star formation, and also black holes in those galaxies, how that changed with time. And so I looked at that for my thesis. After my thesis, I went overseas. So I went to the US for 10 years, and I was based at Harvard for 3 years, and then Hawaii for 7 years. So that's how I got to use those Hawaiian telescopes. And there I started looking at the amount of oxygen in the universe. And so I've been doing that for the last few years. And I came back to Australia in 2011, and multiple reasons I wanted to come back to Australia, but I have 2 kids and they were getting to be school age, and I wanted them to come and do school here in Australia. And we're really happy to be back in Australia, and the kids are happy to be back at school too. Okay, there's another question here. As space is expanding between things, but space is made of nothing, what does increasing mean? Yes, exactly. So it's actually the nothing bit that's getting bigger.
Can I ask another question, Lisa? The people on the Zoom are probably not aware of the James Craig Watson medal that you received. Can you talk about the sort of research that went into that?
Yeah, so the James Craig Watson Medal is a US award awarded by the National Academy of Science in the US, and they've actually been running this medal for about 100 years, and lots and lots of people have been awarded this medal over that time, but nobody in the Southern Hemisphere. So I was the first person in the Southern Hemisphere to get that award. The research that I did to get that award was in a couple of different areas. So it was my research on the oxygen history of the universe. So not only did I measure the amount of oxygen in the universe with time, but also I created the tools to do the measurement of the oxygen. So when I first started doing this, there really wasn't a very reliable method to measure the amount of oxygen. And so what I did was I used theoretical models. So I used models of star formation, and then I used models of gas around those stars. And then I calculated the relationship between the spectra that we see, so the emission lines that we get from the oxygen, and the relationship between that and the total amount of oxygen in a whole star cluster. And then, and I made those models so that you could apply them to either clusters of stars and the gas around it, or galaxies. And so I published that as well and put it out there for other astronomers to use like a tool. And so other astronomers found that really helpful, and lots of astronomers used those tools. And then I had the tool then to measure the amount of oxygen. Then I could measure the amount of oxygen. And I did that in other areas as well. So I also looked at the amount of light in galaxies from supermassive black holes and versus the amount of light from star formation in galaxies. And I developed the tools to measure those using these models as well. So I used models of gas around light from black holes, and I used models of gas of light from around star clusters. And I also looked at the amount of star formation and supermassive black holes in colliding galaxies as well. And so I think the award is really because I used the theoretical models first, developed the tools, then applied the tools to the observations, and I got my own observations of galaxies to apply the models to. So it's a pretty long-term project. I'm basically building, getting ready to be able to make those discoveries, and then finally using them to make the discoveries. And so I had a real big picture, big goals, and then I just worked towards those goals, and it was all exciting all along the way. So and so I think that's why I got the award.
Nice work, Lisa. Yeah, and it's great to get that recognition for you and the work you've done. I've got a few students in my physics class that use computer simulations, and I'm very much not very good at them. And so, you use the supercomputer based at ANU.
Yeah, so we use the supercomputer. It's called the National Computational Infrastructure, and so it's a big supercomputer based at ANU. And then we also use clusters of smaller computers within our astronomy department. We've got a smaller computer cluster. It's still, these are big computers set up in their own room. It needs to be air conditioned all the time because they create a lot of heat. And so, yeah, these are the best computers to use. But some of my smaller models actually can run on a laptop. So I do run them on my laptop that I'm talking to you on today as well. So we use a combination of different computers.
And yeah, really cool to hear that you're an NYSF graduate.
Yeah, so I had a fantastic experience at NYSF, and I would strongly encourage high school students interested in science to go, because you just have a great time. You get to meet all these other students from across Australia, and it's an amazing opportunity. You get to go do tours of different labs and different departments, and like we went to Mount Stromlo, and you just get to see a huge range of research that's happening in Australia. It's really eye-opening, like the cutting edge stuff that people are doing in all the different areas. And it really inspired me to work hard in year 12 so I could get into, Bachelor of Science and at Adelaide, and, do what I needed to do to become an astronomer.
Well, thank you once again, Lisa, for joining us today and your presentation. I like, contextualizing not just the oxygen, but yeah, the fact that it had an interesting past on our planet. We had it, but it wasn't available, and then it was, and then it reacted. Checkered history.
Yeah, it has, and so we're lucky to be alive, because it could have been that ice age actually killed all the cyanobacteria. So I think it's a really wonderful story, the story of oxygen, and yeah, it's just worth knowing. And when you're breathing in deeply, you can just think, oh, we're lucky to be alive. We're really lucky to be alive. And these atoms were created 12 billion years ago, and now here they are on our Earth and able to be breathed by us.
Well, thank you very much, Lisa. I'd like to thank you on behalf of my students here in Tamworth, but all the students around New South Wales that are joining us for our ASTRO 3D depth study.
Okay, thanks very much, Matt. Thanks very much, everybody, and I hope you enjoy the rest of your day depth study.
Thanks, Lisa. Bye.
Thank you. Bye.